You ever stop and think about the fact that right now, inside your chest, there's this silent, invisible electrical storm happening every single second? It's the current that's literally powering your life, but you can't see it or feel it. So, how do we actually listen in on this body electric? Well, that's exactly what we're about to dive into. You see, your heart is so much more than just a muscle. It's really its own little electrical generator. It all kicks off in this tiny spot called the sinoatrial node, or SA node for short. That's the heart's natural pacemaker. And when that SA node fires, it sends this electrical wave just cascading through the heart's chambers, telling them to contract in this perfect life-sustaining rhythm. But here's the catch. That electrical signal is minuscule, and it's buried deep inside your body. So how in the world can we pick up that faint whisper through all the layers of muscle, bone, and skin? That is the big question we're going to answer as we follow the journey of this signal from the inside out. All right, so our first stop on this journey is to really understand the invisible electric field that this tiny signal creates. All that coordinated electrical activity generates an electric field that radiates out through your entire torso. Now, for any given moment in the heartbeat, we can think of this field as a dipole. It's like having a tiny little battery in your chest with a positive and negative end that's constantly tumbling and changing its strength and direction. And it's this moving, tumbling field that creates tiny, and I mean tiny, voltage differences all across the surface of your skin. And when I say tiny, I am not kidding. Which brings us to our next huge challenge. By the time that signal actually makes it to the skin, it is incredibly weak. We're talking millivolts. So to make any sense of it at all, these biopotential signals have to be amplified about 1,000 times. Yeah, 1,000. Without that massive boost, the heartbeat's electrical signature would just be completely lost in the noise. So to capture that super faint signal, we use something called a lead. Now, when I say lead, you might be picturing a physical wire, but a lead is actually a concept. It's a specific viewpoint created by a pair of electrodes. You can think of each lead as its own unique camera angle, measuring the voltage difference between two specific points on the body to get a particular look at the heart's electrical activity. But here's the thing. Just like you can't really understand a sculpture by looking at a single photo, one view of the heart's electrical field just isn't enough. We need a much more complete picture. Historically, this all started with Willem Einthoven's absolutely brilliant idea. He figured that by placing electrodes on the right arm, and left leg, he could create 3 limb leads that formed a triangle around the heart. This gave doctors the first ever 2D electrical snapshot of the heart's activity in what's called the frontal plane. It was revolutionary. Building on that original concept, today we use what's called a standard 12-lead ECG. This system uses electrodes on both the limbs and across the chest to generate 12 different views all at the same time. By combining all those different angles, we can build this rich, 3-dimensional electrical map of the heart, which lets doctors pinpoint problems with just incredible precision. But you know what? None of this advanced mapping, none of these fancy algorithms, none of it matters if we can't get a good signal in the first place. So let's zoom all the way in on the most critical and honestly the most overlooked part of this entire system. Because here's the bottom line. Everything, the amplification, the 12 different views, all the complex analysis, it all hinges on the quality of the connection at that one tiny point where a metal electrode touches your skin. If that connection is bad, the signal is basically garbage. Simple as that. And that brings us to the 2 main technologies that engineers have developed to try and master this critical interface. So you have wet electrodes and dry electrodes. The fundamental difference between them is really, really simple. A wet electrode, the one on the left, uses a conductive gel to bridge the gap between the metal and your skin. A dry electrode, on the right, makes direct physical contact. Gel or no gel. That simple difference changes absolutely everything. So let's break down the core trade-off here. Wet electrodes, all thanks to that gel, create a connection with very low electrical resistance, or what we call impedance. And that means you get a beautiful, clean, high-quality signal. The downside? Well, they're messy, they take time to prep the skin, and that gel can dry out or even irritate your skin. Dry electrodes are the complete opposite. They're fast, clean, super convenient. But because they're making direct contact with the skin's dry outer layer, they have much higher impedance, which makes them way more likely to pick up noise and interference. These diagrams really show us why this happens on an electrical level. Think of the skin's outermost layer as a major roadblock for that tiny electrical signal. The wet electrodes gel basically creates a super low resistance bridge or a highway across that roadblock, letting the signal flow easily. The dry electrode, on the other hand, has to try and fight its way directly through that high resistance layer, which just makes for a much, much noisier journey. So, the big question for engineers, the real holy grail, is this. Can we get the best of both worlds? Can we somehow get the convenience of a dry electrode with the amazing signal quality of a wet one? And that is exactly where the future is headed. Researchers are exploring some absolutely incredible new paths. They're developing new materials like conductive polymers and nanomaterials. They're designing these innovative microstructures that can make better contact with the skin without needing any gel at all. And get this, they're even integrating tiny circuits directly into the electrode itself to clean up and amplify the signal right at the source, before noise even has a chance to creep in. The ultimate goal here is to create sensors that are so comfortable and so reliable that they just disappear into our daily lives, woven into our clothes or worn like a temporary tattoo, which leaves us with a pretty fascinating final thought. As this technology becomes completely seamless and ever-present, what new, really intimate conversations are we going to start having with that silent electrical symphony that's playing out inside of us every single moment of our lives?